In the summer of 1942, in the engine room of a newly commissioned American fleet submarine somewhere in the Atlantic, a chief motor machinist's mate was holding in his cupped hands a piece of metal that had no business existing. It was a gear tooth, one of many. It had sheared clean off the drivetrain of one of the boat's 4 main diesel engines, taking fragments of adjacent cogs with it on the way out. The engine, a double-acting diesel built by a Hamilton, Ohio company called Hooven-Owens-Rentschler, had been running for less than 90 days since commissioning. Now it was dead. The chief carried the fragments forward through the control room, past the watchstanders who said nothing, and up to the captain's cabin. He did not need to explain what he was holding. The captain had already heard the change in the sound. This was not an isolated incident. Across the Atlantic and Pacific theaters in 1942 and 1943, the same scene played out aboard submarine after submarine. Engines seizing, drivetrains shedding gear teeth, crankcase pressures spiking without warning, boats limping into port on auxiliary engines, or not making it to port at all, completing patrols that produced no kills because the primary machinery was too fragile to sustain the demands of war. The record of these failures is not difficult to find. It lives in patrol reports, in after-action reviews, in the testimony of skippers who wrote in language that left nothing ambiguous. One commanding officer, reviewing the performance of the HOR engine across his squadron, eventually summarized the situation in a single sentence that the Naval Submarine League would preserve for decades. He said the HOR engines had saved the Japanese 30 or 40 ships. That sentence is the starting point of this story, because the engine that failed so badly was not an accident of laziness or indifference. It was the product of genuine engineering ambition, of a Navy that had spent 2 decades trying to build a better submarine, and of a procurement decision that looked correct on paper right up until the moment the first gear teeth hit the engine room floor. And the story of how the failure was corrected, of what replaced those engines and why the replacement worked, is a story about the deeper logic of how America built its way to dominance beneath the surface of the Pacific. It begins not in a submarine at all, but in a Cleveland factory in the middle of the 1930s, and in a set of design competitions that would determine which engines would carry the weight of an ocean war neither side had yet declared. If this story is pulling you in, take a second to hit the like button and subscribe, and drop a comment telling me where in the world you're watching from. It means a great deal to know who's listening. To understand why the HOR engine existed, you have to understand the problem the Navy was trying to solve before the war. For most of the 1920s, the American submarine force operated on engines that were, by any honest accounting, inadequate. The S-class boats that had entered service in the years after the First World War carried diesel plants derived from European licenses, built by a small number of domestic contractors, and none of them performed the way the Navy needed them to perform on the ranges and at the speeds the Pacific required. The German submarine diesels captured and studied after the First World War were substantially better. The Bureau of Engineering knew this. They had, at one point, reverse-engineered 2 German M designs directly, producing Navy Bureau clones that were built into some of the later S-boats, an admission of the gap that the official record tries not to dwell on. The T-class fleet submarines built in that same period had been so plagued by torsional vibration in their coupled drive shafts that T1 was decommissioned after 20 months of service. T2 lasted 18 months. 3 expensive hulls retired before they had proven anything except that the engineering problem remained unsolved. The core requirement that drove all of this was strategic. The Pacific is not the Atlantic. A submarine campaign against Japan, which the Navy's war planners had been modeling since at least the 1920s under the succession of War Plan Orange documents, required boats that could transit from Pearl Harbor or the Philippines to Japanese home waters and back without a support stop. That meant 11,000 nautical miles of surface range at 10 knots. It meant weeks on patrol in waters where the enemy controlled the surface and the air. It meant 4 main engines that could be run hard and maintained by an engineman's gang in an engine room barely large enough to stand upright in. Every weight saved, every cubic foot recovered by a more compact engine, translated directly into fuel, torpedoes, or the equipment the crew needed to survive. The engine was not an accessory to the submarine's mission. The engine was what made the mission geometrically possible. Through the 1920s and into the early 30s, the Navy ran a series of development contracts with domestic engine manufacturers, searching for an American design that could match what the Germans had been producing. By 1932, Admiral S. M. Robinson, then chief of the Bureau of Engineering and a strong advocate for diesel propulsion, had narrowed the field. Development contracts went to 5 companies. The tests were severe enough that most of the competitors fell away. Only one engine came through the process at the Naval Engineering Experiment Station in Annapolis with enough promise to justify a production contract. It was built by the Winton Engine Corporation of Cleveland, Ohio, a company that had been doing marine and later locomotive diesel work since before the First World War, and which had been acquired by General Motors in 1930. The Winton design that survived those tests was a 16-cylinder, 2-stroke V engine, designated the Model 201A. It was a significant piece of engineering. Welded steel crankcase, unit injectors, a bore and stroke combination, 8 inches by 10 inches, that produced a compact, relatively high-output package for its time. The 16-cylinder configuration, developing around 1,600 horsepower at 750 revolutions per minute, was the right size for the 4-engine installation the Navy intended for its new fleet submarines. The first ocean-spanning fleet boat with these Winton V16 diesels was commissioned in 1935. Others followed through the late 30s, forming the backbone of what would become the Gunnel and Below-class programs. The Winton engine was not perfect. The Model 201A went through iterations, with the Navy eventually replacing early installations of the 201A with the improved Model 248 as field experience accumulated. Between 1937 and 1943, the 16248 would go into 55 United States Navy fleet submarines, rated at 1,600 horsepower at 750 revolutions per minute. Further refinement would produce the Model 278 and eventually the 16278A, each generation incremental, each generation tested. What Winton and its successor organization, the Cleveland Diesel Engine Division of General Motors, had built over those 15 years was not just an engine. It was a knowledge base, an institutional understanding of what 2-stroke marine diesel design required and what it did not tolerate. The engineers in Cleveland knew where the failure modes lived. The Navy, however, was simultaneously pursuing a different engine family entirely. The Hooven-Owens-Rentschler Company of Hamilton, Ohio had developed a double-acting diesel, a design in which combustion took place on both sides of the piston rather than just the top. This gave the HOR engine a power-to-weight ratio that, on paper, was remarkable. Every stroke was a power stroke. The combustion chamber above the piston and the one below it fired in alternation, and the result was an engine that could theoretically deliver nearly twice the output in a given physical envelope compared to a conventional single-acting design. The Navy's procurement mathematics were straightforward. More power in the same volume meant more capability in a hull that was already constrained by every dimension. The first HOR engine went into the Salmon in 1938. What the paper calculation did not fully account for was the mechanical complexity the double-acting arrangement imposed. Every piston had a rod rigidly attached to it that passed through a sliding seal at the lower end of the cylinder, connecting down to a crosshead, and then to a conventional connecting rod below. This was not a new configuration in large marine and stationary diesel practice. It had been used for decades in big slow-turning engines where precise manufacturing tolerances and continuous maintenance access were facts of life. In a submarine diesel, which had to sustain high output for extended periods, in a space where access for repair was severely constrained, with gear trains and internal components that could not be swapped out mid-patrol, the design imposed demands it could not reliably meet. The internal gearing in particular, which synchronized the complex motion of the crossheads and connecting rods, had been manufactured with microcracks in the castings that stress and vibration exposed at the worst possible time. The HOR company had not fully solved the sealing problems where the piston rod passed through the lower cylinder face. The heat management through the system created stresses that accumulated in places the engineers had not fully mapped. The Pompano, one of the early Porpoise-class boats to receive HOR engines, did not even make it out of the yard during sea trials before all 4 engines wrecked themselves. Excessive vibration and improperly forged gearing destroyed the drive trains before the boat had fired a single torpedo. The engines were removed and sent back to the factory in Hamilton. On the test stand there, they failed again. The Pompano sat at Mare Island for over 8 months while the Navy and HOR worked through the problems, an entire boat out of service before the war had begun. The name of the engine lent itself to the profanity of the men who served it. In the engine rooms of HOR-equipped boats, the abbreviation was spoken with a vowel change that expressed the crew's assessment precisely. 6 brand-new Gunnel-class submarines with HOR engines were dispatched in the summer of 1942 to the Submarine Squadron 50, based at Rosneath, Scotland, to patrol the Bay of Biscay and support the Operation Torch landings. These boats conducted 27 war patrols between them without claiming a single verified sinking. The combined engine problems kept the squadron operating below the standard the Pacific Campaign would have demanded of the same hulls. When the boats were eventually recalled and transferred to the Pacific in mid-1943, the re-engining that followed represented an acknowledgement that the original procurement decision had cost the Navy the combat output of 6 fleet submarines for 12 months of active operations in a theater where the target set was rich and the intelligence was often ahead of the available boats. When the war did begin at scale, the accounting became undeniable. The HOR engines went into 21 fleet submarines in total. The pattern that emerged across those boats was consistent. The engines performed erratically in service, producing the kind of failures that could not be managed through watch-standing discipline or engineman skill. They shed gear teeth. They produced explosive pressure spikes in crankcases. They leaked through the crosshead seals in ways that contaminated the lubricating oil system. A boat running at speed on the surface, which a fleet submarine needed to do to reach patrol areas, position for attack, and escape counterattack, was running those engines at or near their limits. The limits turned out to be lower than the specifications promised. The USS Gunnel, commissioned in August of 1942 under Lieutenant Commander John S. McCain, Jr., went to sea on her first war patrol in October of that year, attached to the Western Naval Task Force for Operation Torch, the Allied landings in North Africa. Gunnel performed her mission. She made reconnaissance runs off the Moroccan coast before the landings and used infrared signals to guide the invasion fleet to the beaches. The mission record was clean. The engineering record was not. En route home from Scotland, the drive gears of her HOR main engines failed. The boat completed the final 1,000 nautical miles on her auxiliary diesel engine. By the time the final swap was complete, the American submarine force had lost the use of those hulls for months at a time across 2 years of the most critical period of the Pacific War. The engineering record does not speculate about what those boats might have accomplished. The patrol logs and the after-action reports simply show the gaps, the months in overhaul, the patrols that never happened. What does survive is the physical evidence of what came after. The Cleveland Diesel Engine Division built its production facility in Cleveland, and in 1942 the Navy helped finance a new government-owned, company-operated plant in Brooklyn, Ohio that expanded capacity to meet wartime demand. The production line that ran through that facility and the original Cleveland plant produced engines that powered submarines, destroyer escorts, and auxiliary vessels across both oceans for the duration of the war and years beyond it. The 16278A went into fleet boats. Smaller Cleveland diesel models went into destroyer escorts and landing craft and minesweepers, an industrial architecture of diesel propulsion that underpinned the entire American naval presence in both theaters. Daniel Noble, the engineer who had argued for FM radio in the infantry's backpack, worked in a different domain from the Cleveland diesel engineers, but the logic was the same. A field that had accumulated real-world testing data, that had integrated its failure lessons into successive designs, produced systems that worked when the lives of the men using them depended on the systems working. The GM Cleveland diesel engineers had 15 years of incremental work behind the 16278A. The HOR had ambitious theory and insufficient testing time. The war settled the argument with the kind of clarity that no engineering review board ever matches. The USS Bowfin, commissioned in May of 1943 and powered by 4 General Motors Cleveland diesel engines, completed 6 war patrols and was credited with sinking 16 Japanese vessels. The boat is preserved today at Pearl Harbor, the engines still in place. What you're looking at, if you stand in the engine room of the Bowfin, is a 16-cylinder V configuration, the geometry of it straightforward and accessible, a design that conceals in its proportions the entire history of the engine lineage that preceded it. The Bowfin was not exceptional because of the engines. She was exceptional because of the crew, the commanding officers, the tactics, the torpedoes, the intelligence that put her in the right place. But the engines were the reason the patrols could happen at all. The reason the boat could be relied upon to do what a fleet submarine was asked to do for the duration of a 2-month deployment in waters the Japanese Navy and the Japanese Air Forces had been patrolling for 2 years. The chief machinists, mates who ran those engines, knew what they were running. Some of them had served on HOR boats before the re-engining. They understood the comparison directly and personally. The broader record of the American submarine campaign against the Japanese merchant fleet reads like a product specification for what a reliable diesel engine enables. Japanese merchant tonnage sunk by American submarines totaled in the millions of gross tons by war's end. The oil tanker routes from the Dutch East Indies that fed Japanese industry and the Japanese Navy were systematically severed. Japanese convoys were forced into increasingly defensive routing, consuming escort hulls that could not be replaced at the rate they were lost. The strategic analysis conducted after the war by both American and Japanese naval historians concluded that the submarine campaign against Japanese commerce was among the most decisive single components of the American victory in the Pacific. That campaign required boats that could sustain patrols. Patrols required engines that ran. The engine question, which might look like a footnote to a campaign fought with torpedoes and periscopes and radar, was in fact an enabling condition for the entire campaign. The HOR failure was a deduction from that total. The GM and FM replacements were the account being rebuilt. The HOR company itself did not long survive the war. The failure of the submarine engine program was not the only problem the company faced, but it was the most visible and the most consequential. The double-acting principle it had applied was not inherently wrong. Large stationary diesel engines and slow-turning marine plants had used it for decades without the kind of failure cascade the submarine installation produced. What the HOR program demonstrated was that applying a mature principle in a demanding new context required the same testing discipline as developing a new principle from scratch. The company had not performed that work. The Hamilton factory passed through several ownership changes in the post-war years, eventually folding into a succession of mergers that produced no lasting diesel engine legacy for submarine work. The double-acting diesel for submarine use became a chapter in the technical literature rather than a production line, a record of an engineering path that was technically coherent, economically appealing, and operationally disqualifying. The Cleveland Diesel Engine Division of General Motors ran until 1962, when the development of nuclear-powered submarines reduced the Navy's need for high-output marine diesels, and General Motors folded the division into its electromotive operation. The engineers who had refined the Winton lineage through 3 decades of iterations left behind them production record measured in tens of thousands of engines across marine, industrial, and auxiliary applications. The mistake the title describes was real. It was a procurement decision made by intelligent people on the basis of reasonable-looking performance data, in a Navy that was trying to close an engineering gap that had been visible since the 1920s. The double-acting design promised more power and less space, and that promise was genuinely attractive in a hull form as constrained as a submarine. The price of the promise was the testing discipline it had not yet earned. And the price of that shortcut was paid by the men in the engine rooms of 21 boats across 2 years, and by the operational record of what those boats did not accomplish while their machinery was being rebuilt on the pier. She spent months in Portsmouth Naval Shipyard undergoing repairs before she could return to service. After a second patrol in the Pacific that produced further engine casualties, the Gunnel became the first Pearl Harbor-based submarine to have her HOR engines removed and replaced. She was not the last. If this is the kind of history you want more of, subscribe and turn on notifications. There's far more in the record still to cover. Your support is what keeps these stories coming. By late 1942, Vice Admiral Charles Lockwood, commanding submarine operations in the Pacific, had seen enough. 12 boats with HOR engines were pulled from fleet service and scheduled for re-engining at Mare Island. The commander responsible for issuing movement orders based on magic intelligence intercepts, Commander Richard Vogue, found himself with more targets being generated by signals intelligence than he had serviceable submarines to assign. The gap between what the intelligence was identifying and what the available force could act upon was a direct cost to the engine failures. Decisions about target assignments, about which boats would be sent to which patrol areas, were being made against a backdrop of reduced operational hulls. The operational record does not speculate about the ships that were not sunk, because boats were in overhaul. It simply shows the gap between the intelligence that was available and the submarines that were available to act on it. The replacement engines that went into the re-engined boats were General Motors Cleveland Diesel 16278A units or Fairbanks-Morse Opposed-Piston engines, both designs that had been refined through exactly the years of iterative testing that the HOR had bypassed. The 16278A was a 16-cylinder, V-type, two-stroke engine with a bore of 8 3/4 inches and a stroke of 10.5 inches, rated at 1,600 brake horsepower at 750 revolutions per minute. It was air-started. The design was a direct descendant of the Winton 201A lineage, every generation incorporating lessons from the previous one. Where the 201A had exhibited reliability issues in early fleet submarine service, those failures have been studied, understood, and corrected in the 248 and then the 278 series. The men who built these engines and the engineers at Cleveland who refined them knew exactly which components failed under what conditions and had built the answers into the successor designs. There was no theoretical elegance driving the 16278A. There was only a very long list of things that had broken before and had been fixed. Between 1937 and 1943 alone, the 16248 variant had gone into 55 Navy fleet submarines. The production infrastructure behind it, the Cleveland plant, and the wartime expansion facility in Brooklyn, Ohio that the Navy helped finance in early 1942, was already mature when the HOR boats began arriving for overhaul. The supply chain for the GM engine's components existed. The technical manuals for its maintenance were written. The training for the engine men who would run it was established. When a boat came in for re-engineering, the path from the old engine to the new one was well understood, because the new engine had been in continuous production and continuous service for years. The HOR replacement, when it finally came, did not require the Navy to solve any new problems. It required the Navy to install the solution it had been building since 1932. The Fairbanks-Morse Opposed-Piston design occupied a different engineering tradition entirely. Built under a Junkers license, it used a single cylinder with pistons entering from both ends and no cylinder head, the two pistons sharing a single combustion chamber and driving two crankshafts, one above and one below. It had its own early difficulties, documented with the same candor the submarine force applied to all its engineering problems. But by the time it went into fleet service in numbers, it had been worked into a reliable configuration. The 10-cylinder, opposed-piston Fairbanks-Morse, running at 720 revolutions per minute, would go on to power a majority of the Cold War-era American submarine fleet into the 1960s, a persistence that speaks to the quality of the mature design. What the record shows, across the boats re-engined through 1943 and 1944, is the difference reliability makes in wartime. The Gunnel and Below-class submarines powered by the Cleveland GM diesels and the Fairbanks-Morse engines could sustain the operational tempo the Pacific required. Patrols of 75 days, transiting thousands of miles on the surface, diving and surfacing repeatedly through enemy-controlled waters, running at full power during attacks and full power during evasion, placed demands on the machinery that the HOR could not meet and that the GM and FM engines, at the point the war reached its mid-period, could. The record of the Gunnel-class boats with reliable engines is the record of the American submarine campaign against the Japanese merchant fleet. The Flasher, the Rasher, the Barb, boats that sank hundreds of thousands of tons of Japanese shipping, severed supply lines across the Western Pacific, and drove the Japanese convoy system into increasingly desperate defensive configurations. That campaign was not won by any single weapon or tactic, but it required the machinery to work. There is something the German post-war technical observers noted, reviewing the American submarine program in comparison with their own. The United States had entered the war without the most elegant engineering in any given category. The HOR engine had been the attempt at elegant engineering, and it had failed. What replaced it was not elegant. It was iterative. It was the product of a process that treated every failure as a data point to be incorporated rather than a setback to be minimized. The Winton engine lineage, from the 201A through the 248 to the 278A, is a 15-year record of incremental refinement. The kind of process that does not produce breakthroughs. The kind of process that produces engines that do not shed their gear teeth in the engine room of a submarine off the coast of Japan at 3 in the morning. The last of the 21 HOR boats was not fully re-engined until the middle of 1944. The men who replaced those engines, the machinists, mates who worked in the overhaul bays at Mare Island and Portsmouth, the engineers at Cleveland who had been refining the successor design for 15 years before anyone needed it to work in combat, did not receive medals. The Navy does not medal a production line. The record of what the 16278A contributed to the Pacific submarine campaign is embedded in the patrol logs of every Gunnel and Below class boat that ran the engine from commissioning to the end of the war without losing a patrol to mechanical failure. The evidence is statistical rather than narrative. It is the absence of the kind of entries that appear in the HOR boats' records, the engine room casualties, the power losses, the repairs completed under operational pressure with parts that weren't quite right. The absence of those entries is the testimony the record offers for the engines that worked. The gear tooth the Chief carried forward in 1942 is not a preserved artifact. The engine it came from was cut out of the boat at Mare Island and scrapped. What replaced it ran reliably until the end of the war and for some years beyond it. The boat went on to complete war patrols. The crew went home. Most of them never talked much about the engine room. That is generally how it goes with the machinery that wins wars. It works, and because it works, nobody writes it down. Thank you for staying with this until the end. If what you heard here stayed with you, the other films on your screen carry the story forward. Subscribe if you haven't, and I'll see you in the next one.